You copy the properties of bases before I left, but just quickly running through it. An acid and a base, in some ways they are very similar, and in other ways they are polar opposites. The thing that they're polar opposites is because they will neutralize each other and produce a salt. But like an acid, all bases are electrolytes. Whether it's a strong or weak base doesn't matter. But the stronger the base, the closer it is to a pH of 14 or a pOH of 1, the stronger the base, the better conductor it is, the better electrolyte it is. And all an electrolyte, again, is something that completely disassociates into ions when it's dissolved in water. All strong acids will ionize in water. All strong bases will ionize in water, as well as salts will ionize in water. So salts are electrolytes as well. So electrolyte, if it's a strong base, is a good conductor, meaning we stick a little conductivity meter in there and it's going to light up brightly. If it's not a good conductor, it won't light as bright, and if it's not a conductor at all, then it won't light up at all. All right. So acids had a sour taste, base have a bitter taste. Caustic basically means that they cause problems in our biological systems. So just kind of know that. They feel slippery. Most bases are at least one component of soaps, so they're going to have that kind of slippery feel like a soap. If you've ever, I don't know, let me think. Even like milk tends to be slightly basic. So if you just take like milk in between your fingers, you can kind of feel it slippery and all of that. Or milk when it's hardened like cheese is very basic. Things like that. Coffee is a base as well. Coffee and beer and all of those things. All right. They react with acids to form water and a salt, and they react with indicators. Some indicators indicate for acids, and they're going to change a certain color. Other indicators react just for a base, and they'll change to a certain color. So for a base, we'll use red indicator strips, and they will turn blue. For an acid, we would use a blue indicator strip, and it will turn red. If you take an indicator strip that you determined a base that turns blue, and then you stick it, then you let it dry, and then you stick it in an acid, it'll turn back red. All an indicator is a chemical compound that reacts with a certain pH or pOH. Then there's like a universal indicator like phenolphthalein that will go from yellow to pink. And then the pH values are between 7.1 and 14. This is a liquid indicator. And then I also have, with the little probeware stuff that I have what's called a pH meter. And basically it gives me the hard numbers. I'm getting to where I use this more than any of these, because these don't give you an absolute value of pH. You have to guess at it, whereas this one gives you an absolute pH value. Yes. Weaker one would be a lighter blue. Stronger one would be a closer to purple. And then there's other indicators other than phenolphthalein. I think on the first page of your thing, it lists. It just does that. In our textbook, we have a list of about 10 indicators that we can use at different ranges, and I'll point that out. All right, so let's continue moving forward. So yesterday, or on the slides for both acids and bases, we identified a salt, and we've talked about this before in class. Just remember that a salt is a metal that is combined with a halogen. For the most part, all acids will have a hydrogen that it can donate, and then it's going to have either a negative polyatomic ion or a halogen like fluorine, chlorine, bromine. And whenever you react an acid, the hydrogen in that negative polyatomic ion, with a base, and the base is typically going to have a hydroxide ion, OH, and some metal attached to it. So like sodium hydroxide is a very strong base. When you react with that, the sodium then combines with the chlorine, fluorine, or bromine to make a salt. So a salt is an ionic compound that does not produce a hydrogen ion or OH ion when it's dissolved. So, for example, if we combine, can everybody see that black writing? If we combine HCl, which is a strong acid, with sodium hydroxide, which is a strong base, it no, that's worse. Yellow doesn't work. HCl plus NaOH reacts to form. So the hydrogen is going to replace the sodium, and the sodium is going to replace the hydrogen. So we have NaCl plus HOH, which is also H2O water. So whenever a strong acid reacts with a strong base, your product is water and some sort of salt. In this case, this one actually makes table salt. So, I guess this is a really long time ago now. In my mind, it's not that long ago. It's probably about 10, 15 years now. But right there on the racetrack on Airline Highway in St. Rose, there was a tanker truck that was hauling hydrochloric acid that overturned right there, right before you get to the racetrack. Spilled that acid all over the road, and basically they came with baking soda, which is sodium bicarbonate, which is a base as well, and the end product was sodium carbonate salt and water. So you basically had salt water just right there, and that's why that little area in front of that little restaurant that keeps going out of business, that's why the grass there is still always just kind of dead, because the salt content was too high there and it killed all the plant life, and this lasted for a few years. But it was better than exposing that environment to the hydrochloric acid. Yeah, they just nobody I don't think anybody knows they exist. Yeah, it's a restaurant, just something. It was a building that has had several different restaurants. All right. So anyway, that's what we need to know about a salt. Now, reason why a salt is important is because every time we react an acid and a base, we do something called a neutralization reaction. So, and the whole thing, the reason why I brought up the part about racetrack, it stands out in my mind because I actually saw this event happen. Like, I was getting gas at racetrack and I was kind of stuck there because they blocked it off and you couldn't move until they took care of the spill. So, neutralization reaction between an acid will react with a base to produce salt and water. There's three ways that we can express a neutralization reaction. A word equation, which is basically, we would say hydrochloric acid plus plus sodium hydroxide yields sodium chloride and water. All right. Formula equation, again, would just be what we did earlier. HCl plus NaOH. And there are other acids and bases other than hydrochloric acid and sodium hydroxide. I'm just using this one because it is easy. NaCl plus H2O. All right. And then we're going to do something called a net ionic equation. And I will show you how that works in just a moment. I'm not going to ask you to produce net ionics, but what I want you to see is what happens to these acids and bases as they're reacting in water. All right, so a net ionic equation has only the ions that have taken part in the reaction. In the reaction, the ions that do not change are omitted. These ions are called spectator ions, so they don't really take part in the reaction. So we're going to look at a chemical reaction, and we'll get rid of the spectators. And this has to do with what things are soluble and insoluble in water, and all of that. We have an acid plus a base is going to yield water and a salt. So we've been using hydrochloric acid and sodium hydroxide, which produces water and sodium chloride. All right, so we know up until this point, we've seen everything in here. Now, I mentioned this yesterday. What type or what class or what phase do we consider acids and bases? Aqueous. So when something is aqueous, that means it's dissolved in water or it's in a water-based solution. So hydrochloric acid and sodium hydroxide are both aqueous. Water is a liquid, and sodium chloride, will it dissolve in water? Will table salt dissolve in water? Yes. So that is going to be aqueous as well. All right. The reason why that's important is it lets us know what things are ions when they're dissolved and what things aren't. So if we write this as a complete ionic equation, that means we're going to separate everything that's aqueous into ions. And you started seeing me do this yesterday whenever I showed you the chemical equation for copper 2 sulfate dissolving in water. We started doing a complete ionic equation there and net ionic. So hydrogen chloride is aqueous, so it's going to break into a hydrogen ion and a chlorine ion. Plus sodium hydroxide, which is aqueous, so we have a sodium ion and an OH ion. Now, notice that I have the positive and negative charges there. Hydrogen is a +1, chlorine is a -1, sodium's a +1, and hydroxide's a -1. I didn't write the ones because the plus or the minus was sufficient there. If it was a charge like +2, then I would have shown a +2. So if we had something like magnesium chloride and sodium hydroxide, then we would have had that +2. All right. Now, on the product side, we form water. Why didn't I write water as ions there? It's not aqueous. What type of compound is H2O? Is it covalent or ionic? Covalent. Water is a covalent molecule. Covalent molecules do not ionize. So water is going to be written as the compound. But sodium chloride was aqueous, so we write that as ions. Sodium, which is aqueous, and chlorine, which is aqueous. Now, you might notice, so we're going to move from complete ionic to net ionic, and for some reason red is even worse than white. All right, we're moving from complete ionic to net ionic, and what we do with net ionic is we get rid of the spectators. So anything that looks exactly the same in the reactant and the product, we cross out. So I have a chlorine on this side, so I'm going to scratch it out, and I have a chlorine on this side. I have a sodium and a sodium, so I scratch out the sodium and the sodium. And then what we do is look and see what's left over in this reaction is we have a hydrogen ion plus a hydroxide ion that reacts to form H2O. And what I will say about this is any reaction between a strong acid and strong base the net ionic equation will look just like this. So anytime we have a reaction between a strong acid and a strong base, the net ionic equation is going to be a hydrogen plus a hydroxide yielding to form water. When it's a weak acid and a weak base, then there's some partial dissociation, that there's some things that don't always end up as clean, and so you'll have some other things that aren't spectators involved. But in a strong acid and a strong base, you'll just have hydrogen and a hydroxide forming water. So moving over, the water molecule stays the same because water is a covalent compound, so it doesn't dissociate. And then we have 2 sodiums and 1 sulfate. And then coming back to it, we cancel out the things that are the same on each side. So sulfate is exactly the same on each side. Sodium is exactly the same on each side. So what is our net ionic equation? We have 2 hydrogens plus 2 oxygens yields 2 waters, and we really could, if we wanted to, we could reduce this one to H plus plus OH negative. And also notice that my arrows on this one, my yield sign is a double-headed arrow because we're talking about equilibrium reactions, whereas these go back and forth. It's not this is a reaction that continues to back and forth until forever. It doesn't ever stop unless I make it stop. All right, so let's get off of that. All right, So just write this guy's name down, Arrhenius. All right. So the Arrhenius theory of acids and bases. The definition of an Arrhenius acid is a substance that ionizes in water to give off hydrogen ions. All right. Whenever hydrogen ionizes in water, that extra hydrogen is going to form a hydrogen bond between the water and the hydrogen to form H3O, which is hydronium. So when I'm doing this in this class, sometimes you'll see me write it as H plus, or sometimes you'll see me write it as H3O plus. That is the same thing when we're dealing with acids and bases. We're just looking at, does this give up a hydrogen ion in solution? And if it gives up a hydrogen ion in solution, then it is defined as an acid. So acidic solutions are formed when an acid transfers a proton to water. So if we have hydrochloric acid that is a solid hydrogen chloride or gaseous hydrogen chloride, is not considered an acid at that point. But when we dissolve it in water, it becomes hydrochloric acid, so it gives up a hydrogen ion and a chlorine ion. Necessarily write this one down because all I'm just showing you is how the hydronium ion forms. So when we're looking at this one, remember the hydrogen chloride is going to dissociate into H plus and Cl minus, right? So this hydrochloric acid is going to give away this hydronium to the water. So it reacts with the water, and the new compound that's formed is H3O. And remember, oxygen is a -2 and hydrogen is a +1. So we have an overall charge to this compound of a +1 plus the chlorine ion. All right. So the important thing is because the acid is always dissolved in water, that hydrogen combines with the water to form hydronium, which is the acid version of water. All right, the acidic version of water. All right. So again, I didn't really want you to copy anything off of that one. I just wanted you to kind of understand why this and this are the same thing in our terms. Remember, all acids are always dissolved in water. They're always in solution. So this hydronium always exists. But for the most part, I'm just going to say hydrogen ion because that's the accepted thing. All right. Now, so we had an Arrhenius acid. Now let's look at an Arrhenius base. An Arrhenius base is something that ionizes in water to produce hydroxide. All right. So examples of Arrhenius bases are things like sodium hydroxide and ammonia. All right. So sodium hydroxide dissociates in water and it becomes a sodium ion and a hydroxide ion. All right. Now ammonia, we add ammonia to water. And so like if you've ever been in a hospital or the bathrooms right after they are cleaned, they use an ammonia-based cleaner in our bathrooms. It's a very strong odor. but when ammonia is dissolved in water, it produces, ammonium. When ammonia is dissolved in water, it produces ammonium, which is NH4 plus OH. And essentially what happens here is water gives away one of its hydrogen ions to ammonia. All right, so this stops being H2O and becomes HO or OH. All right, so remember yesterday that we said that water can act as either an acid or a base. In this case, the water is acting like an acid, reacting with the base that's there, which is ammonia. Oh no, I'm just looking at something. I need to pick that up. All right, anybody need more time? Moving on. All right, Bronsted-Lowry acids. This is where I wanted to get. A Bronsted-Lowry acid is what's called a... So Arrhenius and Bronsted-Lowry, Arrhenius was working kind of on his own. Bronsted-Lowry was a couple of scientists working together. And they both came about and defined acids very similarly at the same time. The only difference is Bronsted-Lowry, rather than identifying hydrogen as the primary component of an acid, Bronsted-Lowry said that it's a proton donor. So think about a hydrogen atom. What is essentially a hydrogen, or what a hydrogen ion? What is it? So if we look at hydrogen, it has one proton, it has 0 neutrons, and when it has an electron, it has 1 electron. But if we make hydrogen an ion, we get rid of that electron. So what is hydrogen? Hydrogen is a proton. So a hydrogen ion is essentially a proton. That's why Bronsted-Lowry defined an acid as a molecular ion that is a proton donor. It's going to donate 1 proton to water to form hydronium. All right. In Bronsted-Lowry, we also have something called, we have a Bronsted-Lowry base as well. Bronsted-Lowry base is a molecular ion that accepts a proton. So you have one substance that's going to give away a proton, and then you have another substance that's going to allow it to come in and be part of its compound. So since we have these two, in the chemical reaction, we also have something called a conjugate base and a conjugate acid. So conjugate base is the species that remains after the Bronsted-Lowry acid has given up its proton. So after that acid gave away the hydrogen, whatever's left over is your conjugate base, because now it can accept a proton. And whatever's left over after the proton has been accepted, or whatever new compound is formed after the proton has been accepted, becomes the conjugate acid. So I'll show you this with some examples, but let me take care of something real quick. I'm not going to show you a demo. I'm going to show you on chemical. So I know it's kind of hard to see, but all right. So what I want you to do is go ahead, copy down this, and it's hard to see, but basically it is. H2O plus H2O reacts to form H3O plus OH. All right. Yeah, all we're doing is labeling conjugate acid, conjugate base. Now, this one's kind of funny because we have water plus water yielding to react hydronium and hydroxide. This is always happening in a sample of water all the time. It's going back and forth between acid and base and all of that, and that's why pure water is neutral, because this equilibrium reaction occurs at a set rate that it's always in equal parts. So what we're saying here is this hydrogen is being donated to that water molecule to make H3O. So this is the proton donor. So this is our acid. This is the proton acceptor. So this is our base. Now this becomes our conjugate acid, and this becomes our conjugate base. All right. Now, so this is our acid because this was our original one that's going to give away the ion, the proton. All right. Why am I calling this a base now? What does it have the ability to do? Why does it have the ability to accept a proton? What is its charge? -1. So a -1 charge wants to gain what? A proton, because a proton is what charge? +1. I'm just trying to see if y'all can reason that out. I know y'all get it, but sometimes those simple things are the things that we miss. All right. This one is H2SO4. That's OH negative. So it forms HSO4 and H2O. All right. So looking at this one, looking at this reaction, which one is going to give away a proton? H2SO4, because we have 2 hydrogens here and only 1 there. So we're giving away the hydrogen to that one. So what are we going to call this one? Is it an acid or a base? That's an acid. This is a base. Now, which one is my conjugate? That should be H3O. No, it's H2O. Which one is my conjugate acid now? All right. This is my conjugate acid because that's the one that gained the proton. And then this is my conjugate base. A lot of times if we can see a negative sign or a positive sign, that makes it easy to tell. I know this copy isn't that great. That's why I don't use it anymore as far as having you do it. All right, let's do one more and then we're going to move into some practice. All right, so we have HSO4 negative plus H3O. Wait. That's a 2. That's a 2. This is a 3. All right. So we have HSO4 negative plus H2O yields to react to form sulfate and hydronium. So which one of these is donating a proton? Which one's getting rid of its profor? All right, so what are we going to call this? An acid. But wait, it's got a negative overall charge and it's still an acid. So know that that can happen. All right, we're just looking for which one gives away its hydrogen. So this hydrogen is going to that. All right, so that makes this our base because it accepts the proton. Now, which one of these is our conjugate acid? Which one can now donate a proton? So that's our conjugate acid. That makes that our conjugate base. All right, let me see one thing just so that I can humor myself. Yep. All right. That's it for notes. Sorry I overloaded y'all with that, but I wanted to get through some material. Yes. All right. Six, 7, 8, 9, 10. Take one, pass it back. 6, 7. Take one, pass it back. Yes. You just have to look and pay attention. Okay, this is what's left over after the hydrogen has left. So that's your conjugate base. So sometimes they'll write it as your conjugate acid ends up here. It just depends. 2, 3, 4, 6, 7. Take one, pass it back. All right. All right. So everybody should have this sheet. I'm going to go through and I'm going to work number 1 and number 2 with you if they've been passed back. Everybody got them? I need one for Logan too. I must have miscounted. Yes. Say again? Yeah. Yes. All right. So let me All right. So let me go ahead and show you what I want you to do on this page. So the things that we're going to identify. We have A is going to represent acid. B is going to represent base. Ca. And Cb. All right. So how are we going to identify this? All right. So we look at this and This is all I want you to do for this side of the worksheet. So we're going to identify which one of these species, and by species, each one, HCO3 plus NH3, that's 2 species. CO3 is a species, and NH4 is a species. Which one of these is going to donate its proton? Which one's going to give away a proton? So, which one, another way to look at this, which one is losing a hydrogen? All right, so this is our acid. That makes this our base. Now, on this side, which one gained the proton? NH4. So this is our conjugate acid. This one is the one that's left over after we've donated it. So that's our conjugate base. All right. Very simple. So all you're going to do is label an A, a B, a CA, and a CB. Pay attention to which way the arrow's facing. If the arrow's facing the other way, then then your acid and base would be on the other side. All right. All right, so on this one, which one is giving up its proton? HCl. So that's our acid. That means this is our base. Now, on this one, which one gained the proton? H3O. So this is our conjugate acid, and that's our conjugate base. That's all we're doing on this. You just have to pay attention to which one gained for the conjugate, you're just looking for which one took on the extra proton, which one took on the extra hydrogen. All right, flip over to the back side. So, write the formulas of the conjugate bases formed by each of the following acids. So, basically, we're looking for what happens to this compound when one of the hydrogens goes away. All right, so how will this compound change when we give away one of the hydrogens? It's just going to be HPO4. All right, and it was already a -1 charge, so what's the overall charge going to be now? -2. All right. So on this one, hydrogen cyanide or cyanic acid. All right. What's going to be the species left over after the hydrogen goes away? All right, so that's all we're doing. I'll give you a hint on number 19. That's the hydrogen that's leaving. Yeah, if you want to rewrite it like that, you can. All right, for 20 through 23, we're saying what happens whenever we have an H plus that's donated to it. So we have fluorine ion, we have a fluorine ion and a hydrogen ion, so it becomes HF. All right, and that's all that's. Well, fluorine's already a negative there. It's kind of hard to see on this copy, but you should be able to see it on your paper. All right, and then moving down to this table, we're just so the acid version of this is H3PO4. The base version of it is H2. PO4 negative. To write the equation, basically what we're saying is that H3PO4 becomes H plus H2PO4 negative. All right. So in all of these, we're just going to determine, basically once we determine the acid and the base, we'll write it as the acid breaks down into the base. So for this one, what would be the acid version of fluorine? HF. So when we break it down, we have HF yields to form hydrogen ion plus fluorine ion. Does that make sense now? Go ahead. You can work on this together. I will be collecting this one tomorrow or at the end of the week, just at some point. So this one is for a grade. Yes. Let me stop this one.